After design innovations, it's now time to look into manufacturing of IMSE. As today's last, but definitely not least presentation, we will hear about automated mass production for IMSE, case ARBURG film insert molding. And this is a joint presentation by Annika Müller from ARBURG and Marko Suva-Anttila from TactoTek.
Hello.
Hello.
And they will walk you through the IMSE mass manufacturing capabilities and present the jointly developed, highly automated injection molding mass production cell, which was introduced at K-Fair 2019 in Germany. And Marko, please take it from here.
For the beginning, I'll walk through the IMSE manufacturing process on high level and split into the 4 main steps. First step is screen printing process, in where decorative, conductive, and dielectric inks will be printed. And during this phase, we will create the wirings, sensors, antennas, contact terminals, and other IMSE relevant electrical features by printing. Once printing step been completed, there will be a surface mounting process, and during this process, electrical components compatible for IMSE structure will be picked and placed into a film. Interconnection is made by using the adhesives. So after this process step, there will be a curing for adhesives, and once the film being cured, there will be a functional testing for a film. During the third step, this flat film with the components will be 3D formed, and it will get the 3D shape. Once this being completed, thermoforming process, these parts will be cut to smaller pieces or laser cut or die cut, so that the film itself fits into a tool during the molding process. Step number 4, which is the final step, will be the injection molding process. And during the injection molding process, 3D formed film will be placed in a tool as an insert, and the final part will be molded. Once this being completed, this part will be electrically tested and it's ready to move to the next phase. And during today's presentation, ARBURG will cover more about this step number 4 during the presentation. And next, I'll go through IMSE part structure. These materials, what we use for the IMSE structure, is verified by the TactoTek, and it consists of materials such as decorative A surface, which carries a film or other film-like natural materials, and decorative inks, which is on top in the picture. Functional B surface, which carries conductive inks, dielectric inks, and SMT electronic components, such as LEDs, for example. And as in this picture, there is a resin, plastic resin in between of A and B surface. And this is something what we call as a two-film structure. So there is a film underneath and the top, or front and back side. But this can be also one film structure, so that either A surface or B surface act as a decorative surface and functional surface at the same time. In today's presentation, we are talking about the one film structure type of application, where A surface carries decorative and electronics properties as back molded part. The part what we used to create this automated manufacturing cell together with ARBURG was named as Nightlight Demonstrator, and I'll describe a few design features of this part. Decorative part of this part consists of black and white decorative surfaces for logos, user interface elements, and illuminated window, and the backside in the middle functional surface which carries conductive inks, traces, capacitive sensors, and 5 pieces of LED components. And this manufacturing demonstrator, what we used to create this production cell, was designed by TactoTek and in collaboration with partners such as DuPont, Covestro, Everlight, Cypress, and some other parties. Film insert, as seen in the picture, is on 3D shape before molding, not on a flat level. It is recommended to form this film before the molding to achieve electrical, aesthetic, dimensional, and electrical characteristics stability. Insert term being used as feeding into a tool is not from the feeder. Typically, it is by the robot. And that's why film will be placed into a tool as an insert. Due to the sensitivity of electrical components, printed sensors, traces, LEDs, it is important to consider proper part handling to avoid part handling related defects. In this specific case, robot gripper, trays, and other equipments were developed in collaboration with ARBURG to make this part handling as robust and error-free as possible, to make sure that the sensitive components, conductive traces, and sensors are not harmed during the process. Injection molding for IMSE follows in general the common injection molding principles, especially for film insert molding type of molding process. Typically, the considered items are related to injection molding gate location, its type and size, how ejector pins are located, how to consider the parting line, and so on. We also need to consider sensitivity of the film, how to grip that before molding, and once the part been removed from the tool, how this part will be handled so that there will be no handling related defects, for example, for the testing process. For all of this, TactoTek has developed additional know-how and expertise, and it's been packaged into the so-called IMSE Builder, which is one of the products which TactoTek licensed to its customers. In today's presentation, TactoTek and ARBURG will present highly automated injection molding mass production cell, which we introduced 2019 at K-Fair show in Germany. This production cell was developed together with both companies' ecosystem to demonstrate IMSE manufacturing mass production capability by using the modern efficient manufacturing system, which is available today. We also demonstrated that IMSE manufacturing does not really require uniquely developed manufacturing processes or special capabilities, hard to find or develop. Solution is available today. It can be modified, developed, and used for the certain specific products, company and industry requirements. If you would like to see the complete IMSE process running and to see TactoTek manufacturing line and other IMSE related information, please visit at TactoTek YouTube account or our website to get more information. And I would like to thank you for your time and attention. Annika Müller from ARBURG will continue the next. So Annika, stage is yours. Thank you.
Thank you, Marco. Hello from me too. As already mentioned, my name is Annika Müller, and I'm working for the application engineering team of the company ARBURG. On the following slides, I'd like to inform you about the application with the IMSE, which we had on the K-Show together with our partner, TactoTek. However, at first, I will start with a few information about ARBURG. On the picture, you can see our headquarters in the Black Forest in Germany. Our headquarters, with an area of 180,000 square meters, is the only production site of the company ARBURG. In 2019, we had a consolidated turnover of 738 million euro, and our export share is about 70%. Worldwide, we are 3,200 employees, and approximately 2,600 of them are working in the headquarters. ARBURG is present in more than 100 countries around the world. In 26 of these countries, we have our own subsidiary. These are marked on the map with the red dots. In the other countries, which are marked with the yellow dots, trading partners represent us. ARBURG is a family-owned company, which was founded in 1923 by Arthur Hehl. Later on, his two sons, Eugen and Karl Hehl, took over. Nowadays, the third generation of the family Hehl and Keinert are the managing partners. Our main product are the horizontal injection molding machines. On the picture, you can see one example of them. They are available with a clamping force from 125 up to 6,500 kilonewton. And the part weight, which can be realized, goes from 0.001 up to 4,270 grams. But there are also some special machines. For example, the vertical machines, the rotary table machines, the cube machines, and multi-component machines. We also provide complete production cells together with our machines. You can see such an example of a production cell on this picture, and later on in more detail at the IMSE application. For such a turnkey solution, ARBURG is a primary contractor for the customer. This means only one contact person for everything. We have more than 25 years of experience in technology consulting, and the system services are available worldwide. In such a project, we are already involved during the product idea. Then, after the definition of the requirements with the customer, we prepare a concept and have an assessment together. After the planning and the building, there's a fully functional test here in our headquarters, not only of the machine, but also of the complete automation. We also support the customer with service during the installation on his side and during the production later on. Our customers are from every sector of the industry, and we also have special experts for these branches to support the customer on the best way possible. To give you a short overview, here are mentioned some of the branches. We also have experts for injection molding for special materials, like silicon processing or powder injection molding, and also for special processes, like micro-injection molding, injection compression molding, and film insert molding, which leads us to our cooperation with TactoTek. And you can already see a cutout of the part in the picture in the middle on the left. Here you can see a complete picture of the part, the nightlight. To give you a first impression of the part, here are some facts about it. The diameter of the part is 128 millimeter, and it was produced in a one-cavity mold. The part weight is 49 grams, and the foil was overmolded with polycarbonate. The nightlight is a sample part to show how functional 3D touch foils can be used for the more and more upcoming digitalization, for example, in the automotive interior. The application was running on an electrical Arounder 470A with a cycle time of 65 seconds. In this case, we overmolded the backside of the foil where all the electric wires and LEDs are located. On this picture, you can see the complete production cell on the K-show. The automation was placed in the clean room cell and equipped with two laminar flow boxes. The first one on the machine over the mold, and the second one over the automation. Through the clean room cell, we can minimize the contamination of the foil. I go into more details about reason later. Here you can see a top view of the machine and the whole automation to give you a short impression of the installation. On the top of the picture, there is the machine with the mold, and you also can see the laminar flow box. Located on the left side, we have the cleaning station, beneath the centering station and the testing station. In the middle, there's the multi-axis robot, and on the corner on the right, the tray server. For this application, we used a high-precision electric machine. And with our machine controller, we can control all the complex processes, not only of the injection molding machine, but also of the automation components. In the mold, we had special film holders to ensure the foil remains in the correct insert position, also during mold closing. And there was also additional mold centering in the mold parting. At first, the completely integrated multi-axis robot has to pick up the pre-produced foils from the trays on the tray server. After this, the foils have to be placed in the centering station to get the correct alignment, so they can be handled with high precision during the whole process. After the correct positioning of the foil in the gripper, it needs to be cleaned. This step is necessary because there can be some contamination of the foil surface, for example, through particles in the environment. And if we don't clean the foils, the particles will cause small visible markings on the surface of the finished part. In case of the IMSE foil, we used ionized air for the cleaning. You can see it on the upper picture. Another possibility is to use a brush. The cleaning method must be specified for each application individually. One benefit is the cleaning takes place during the injection molding cycle of the part before, and therefore it has no influence on the cycle time. After the cleaning of the foil, the gripper inserted into the mold. To handle the foil, we have the possibility to use vacuum or gripper technology, depending on the requirements of the part, or in this case, the foil. Here we used some vacuum cups and sucked up the foil on non-critical points. We also had a centralization between the gripper and the mold to support the perfect insert position. During this step, there is also the possibility to clean the cavity for the next cycle, if this is necessary, for example, from deposits, but it wasn't for this application. Simultaneous to the insert of the foil, the overmolded foil is removed from the mold. We insert the foil on the movable half of the mold and remove the finished part from the fixed half of the mold. After removal of the part, it was placed into the testing station, the white box in the middle of this picture. There we had a 100% quality control of the electric functions. Also, other post-processing steps can be added at this point. For example, the removal of a sprue. So with this machine and automation, we have a safe, reproducible, and economic production for the nightlight. And when the parts leave the automation, there are no post-processing steps needed. They are ready to use. To bring all these single steps in one automated cycle, we'll now have a look on the film of the application. To summarize all the important points of the presentation, I put them together into this tech cloud. And as you have discovered, we work together with the customer or the partner from the beginning of the product idea and also during the production. We participate with our experience, our know-how, and our support throughout the whole time, and it doesn't matter where the customer is. Thank you for your attention.
Right, thank you, Marko, and thank you, Annika, for your excellent presentation. And next up, we have the live Q&A. And now we are live with Marko and Annika.
Hello.
Hello.
Okay, now.
Okay.
Hello.
Hey, Marko. So, audience, please send in your questions via the Q&A box. And we'll now start the Q&A session. And the first question we have is for Marko about the IMSE yield levels. What can you say about those? What are they? Can you give any typical numbers?
Yes. First of all, we are using for the technology mass production equipments and the environments. So expectation, of course, should be on that side and that level. Our own experience based on the requirements what we have today varies in between from, let's say, from the level of 90% to upwards, but we do have also some yield levels which are below of that. And now the important question here is that what are the customer requirements in the end of the day? What is the complexity of the design of the part to be produced, and what kind of use case will be done? So there is no one single number, but let's say the industrial numbers typically to be expected all the way. And so far what we have done in our own production, the numbers are cost-wise and the performance-wise definitely reasonable and something which makes completely sense for the mass production environment.
Okay, thank you, Marko. And then the next question, I think this is for Annika. What was the most challenging part in designing the automated cell for the IMSE part?
I think one challenge was the reconciliation of the gripper with all the automotion components, because in this case we have this high quality foils which we have to handle during the whole process, and with the LEDs on the backside and also the electrical tracks, we have to make sure that we don't damage them through the handling. And so I think this was one of the challenging parts with this automation.
Okay, so there definitely are quite a few things to consider when putting together a cell like this. Thank you, Annika. Then about this is related to the IMSE technology, like some general production rules. What kind of general rules are you following in order to avoid damaging or displacing of the LEDs while thermoforming?
I think that one of the key rules there are really related to handling. Once you load and unload these films during the process, it's really difficult to damage those LEDs by the equipment or the machinery, because the forces which are used against the film comes from the gas. And that's why it's pretty gentle process for the components itself. But what we have seen is probably the handling of the film once you load and unload, and those needs to be done carefully. And probably then how do you transfer the films to the process itself and out from the process. So we are using the stacking and the certain kind of layerings for the films so that those are not touching each other, as an example.
Okay, and to continue on that, what kind of methods are there to hold the film in the mold firmly? during the process?
Multiple. Mechanical holding is one thing. I think we used mechanical and vacuum holding both in this ARBURG cell tooling, so you can hold mechanically the film, and then you can use a vacuum. Most of the cases we use vacuum or combination of mechanical and vacuum holding.
All right, thank you, Marco. Then a question about the manufacturing cell. Could it be adapted to a different production part, or does it need to be rebuilt completely?
Depends, because, for example, the centering station and the cleaning station and also the trays were specified exact for this application, but with some small changes, it can be more or less adapted to another application.
All right, thank you, Annika. Then a couple of questions regarding the cell indeed. How can the removal of the sprue be added in the clean room because of the possible contamination?
If we had to add a post-processing step like the removal of the sprue, where we had to do some milling or trimming, there's mostly an encapsulated cell in or next to the clean room cell. So we put finished parts, in this case with the sprue, in this extra cell and remove the sprue, for example, in this extra cell to minimize the contamination from the trimming, for example.
Thanks, Annika. And then about the nightlight demonstrators, how do you avoid having circuit breakage between the injected body and the connector tail?
Sorry, could you please repeat that question again?
Yeah, about the nightlight demonstrator, how do you avoid having a circuit breakage between the injected body and the connector tail?
In this case, this was done partially by selecting the inks certain way, and this ink selection is not only about the conductive inks, but it's also the other inks carrying the conductive traces. This is the one thing. Also, there has been the certain little let's say trimming type of activities done on the tool side, also to avoid. I believe that the meaning here is that there is not like cutting type of effect on the edge. So it's a combination of this film design, selection of inks, and also the tool design on that specific area.
Okay, thanks, Marco. Then we have a question about the cycle times. What is the current cycling time for this demonstrator ARBURG was showing? And then a continued question on that. What is the biggest size to produce IMSE parts?
The cycle time for this application was 65 seconds. We could have done a little bit more optimization, but we stuck to the 65 seconds because of quality of the part. And the maximum size, it's not really a definition or regulation from our side, maybe from the IMSE side. But you have to keep in mind that the foil, if it gets bigger and bigger, is not so stable anymore. And if you have to do all the transport from the tray to the centering station and forward, you have problems if the film is not stable as it was on this application.
Yes, maybe I say a few words about that. We don't have absolute value for the size, that what is the maximum size. Definitely, partially it is driven by the design, like how complex the geometry of a part, for example, is, and so on. But then there are certain, let's say, rules which are good to understand, like conductive inks conductivity. So if the traces comes very long, for example, then the conductivity of those inks can come to a limitation. Then machinery at some point during the process might cause certain limitations, let's say surface mounting, for example. So the surface mounting machines typically can take certain width of the film, and length can vary. But then if you look at injection molding, for example, then you have a more flexibility and sense of the sizes for the part. But anyways, currently we are not talking about that the IMSC should be used for the roofs or car bumpers. Those are way too big parts for the technology today. If I say roughly some size consideration, I would say in a car, let's say automotive world, something like center console stack size of parts, overhead control panel, for example, door trim sizes like as such, depending on the functionality and the requirements, could be considered for sure.
All right, thanks, Marko. Then another question for Annika about the cavities. So how can the cavity be cleaned?
There are different options. For example, you can use ionized air, which is, for example, added to the gripper itself, or you can use a brush. Normally, such a brush then would be mounted to some side of the mold, or, for example, a CO2 jet. It depends on the sort of the deposit, and also it's normally not needed every cycle. Sometimes it's needed every 10th cycle, sometimes only once an hour. So it depends on how often it's needed and what deposit you want to clean the mold from.
Okay. Thanks, Annika. Then we have a question regarding the IMSC manufacturing process. So does the screen printing, does it have to be done in the same plant than the SMT and the injection molding?
Our proposal is that the screen printing and surface mounting preferably should be done in the same location. And why it is so? There is for example, in the case of the problem solving or potentially adjusting something for the surface mounting or pick and place process, it is much more easier done those in the location where screen printing and surface mounting are located. Those both are typically also in the electrical manufacturing type of environment, so the fit together is kind of quite a natural, but the molding doesn't need to be necessarily in the same building or same plant. Naturally, it's a sensitive film, so the handling comes then more critical. So if the film itself needs to be delivered different location, then you need to consider the packing and handling more carefully.
Thanks, Marko. And then another question about the nightlight demonstrator. Are there conductive adhesives used in this demonstrator?
Yes, LED interconnections are made by two different type of conductive adhesives. Yes.
Okay. And then about the temperature. How about the temperature inside of the IMSC part after a long time running? I think this is about the temperature during the process.
During the manufacturing process?
Yes.
I believe that the most highest temperature will be introduced during the injection molding process. Let's say like if injection molding resin is polycarbonate, like we many times use, then the temperature at some point as a peak value will be around 200, let's say 70, 80 Celsius centigrade roughly for the moment. And then it comes down due to the cooling. Processes before that will be lower temperature. So thermoforming is around the TG point of the formed film, which is somewhere around 160 Celsius centigrade roughly. And then if we go to the curing for the inks, those are low temperature inks. So we are talking about 80 to 100, something around there. And the curing of inks curing of adhesives after SMT or pick and place process is also low temperature process, which is around 100 Celsius centigrade roughly. So injection molding obviously increases the temperature of unit in the last step most highest.
Thanks, Marko. And then another question for Annika. So which classification is needed for the clean room?
It's not a clean room as for a medical application. There is no certification needed, but we need like the ISO 8 or 9 for example, medical application. If the IMSE application is no medical application, if it is a medical application, it's also needed. But we need this clean room because of the contamination I told before. And there's also no FDA certification, for example.
That's correct. So I'll add there that IMSE itself does not necessarily require clean room environment. It really comes from the industry and the application requirements. So as Annika said, if, for example, this application will be used for the medical industry, indeed, there probably will be even some other requirements what needs to be followed. We prefer to produce at TactoTek in clean room environment due to the multiple reasons. First of all, we can keep the environment stable, which always helps in any case. And secondly, we are also making there the sensitive electronics, sensors, and so on. And those are sensitive for contamination and dust and particles and so on. So to avoid the defects which comes from the flying dust and the other particles, then of course clean room type of environment helps and it makes this kind of problems easier to handle and less issues during the testing and so on.
Okay, thank you both. Then can we place the film in both half, cavity and core, in the same time and then inject the resin into mold?
Well, I can say that yes, we call that as a material stack. So the materials are stacked in a certain way. Film can be on the front side of the part or the back side of the part, and that once we go into the molding process, yes, it can be placed into a tool, both cavity and core side if needed during the process, also automatically. And by the way, we do have one customer also available who have built this kind of automated cell already, and it's completely possible and doable process. And then injection molding will be in between the films if there are two film structures, so film is on the both side of the tool.
Okay, and let's take a couple of last questions and stay in the scope of IMSE manufacturing process. So what is the maximum injection pressure that can be applied during the IMSE molding process?
Same pressures like for any other molding processes. So for example, if there is a need to achieve certain like let's say cosmetic requirements or aesthetic quality or reduce the amount of sink marks and keep the dimensions and so on, you need to apply similar pressures like for any other plastic part to achieve the similar effects. And currently we are using the pressures which can be applied to any these approved materials like polycarbonate, what we use, all the range, whatever is giving the needed results for the final quality and the functionality of the part. So we don't have any maximum minimum type of value for the pressure. There is one consideration, of course, but we are taking care of that before the molding, and once we approve the material stack, is that we should use the components in this structure which really can withstand those pressures. And that's critical, of course, so that the pressure applied during the molding is not harming those components inside.
Okay, thanks, Marko. And then the final question we have time for: how are the conductive adhesives applied? Which techniques are used?
We are using dispensing during the surface mounting process. So there are dispensing units. We are using currently hybrid machine. It fits for our purpose. It doesn't need to be like that. It can be a separate dispensing unit before pick and place, and then continue by the placing the components. But currently there will be a dispensing nozzles which apply the glue or adhesive to the film, and those kind of equipments and the adhesives are commonly known in the industry and available nowadays for anybody who is interested about this.
Okay, thank you, Marko, and thank you, Annika, for this Q&A session and for the presentation as well.
Thank you.
Thank you.